Welcome to the 2.4 notes for Math 126, 127. We're going to be looking more at polynomials on this lesson, and specifically we're going to be talking about different strategies for dividing polynomials, as well as some theorems about remainders and factors. And all of this is stuff that is review from Algebra 2, so none of it is brand new. However, these are things that are really worth making sure to reinforce and to kind of go back, revisit, and have a comprehensive view of. So when we're talking about long division, this can be used anytime you are dividing two polynomials. It's very similar to the method when we use it with constants. Just a little bit of terminology when we're talking about division. Whatever's on the denominator is the divisor. This is from QMath. It's a good little picture here. And that goes on the outside of the division symbol. The numerator, what you're dividing into, is the dividend. That is what's written inside. Now, when we do long division with polynomials, it's similar to how we would do it with constants, with just numbers. So let's just review that really quickly. I'm just going to do 8 divided into something that maybe won't go in evenly. I'll do 5,280 a mile. Okay, so 8 into how many feet are in a mile? So what you would do if you're doing long division with numbers is you would start by looking at this divisor and you would compare it to the first number in the dividend. And you would say, how many times will 8 go into 5? Well, it won't fit into 5, which means I need to include another digit here. So how many times would 8 go into 52 without going over is 6. So I would write that. Now notice where I wrote that 6. I write it above the last digit that I'm dividing into. I'm dividing into 52. The 6 is written above the 2. I would then multiply and subtract and bring down. Oh, I guess I wrote something that would go in evenly. As much as I wanted to do a mile, we'll do something different. There we go. I don't want it to go in evenly. So then I'll bring down the next digit. You can only bring down one digit at a time. 8 would go into 44 at most, 5 times without going over. I would multiply 8 times 5, subtract that, bring down another number. 8 goes into 43 5 times. 8 times 5 is 40. You subtract and bring down. This last number, if we're not writing it with decimals, which we're not going to, we're going to be writing these with remainders that are written as fractions. This remainder of 3 is my new dividend. And my divisor of 8 stays. And so 8 into 5,243 will fit in there 655 times with a remainder of 3/8. So we will use the same strategy here. Now I've got the steps written out for you as a reference in words. I'll let you kind of look at that on your own. There's also an example that you could look at. And one of the things that is important about this example is it does demonstrate that both for your divisor and your dividend, you have to have descending terms where no powers of x are skipped. In fact, if there is a missing power, you need to still have a placeholder in there with a 0. And so that would be important. So there's kind of an example here that you could look at on your own. And then again, there's steps written out in words. Okay, so let's try this one. The first one mentioned is my dividend. It is what would be considered the numerator. It's what's going to go inside my division. Now, as I write this out, I am going to look at these powers. If any powers of x are skipped, for example, the power of 2 is skipped, I need to still represent that power with a 0. Now, that would be true if that happens in the dividend on the inside or on the divisor on the outside. This divisor doesn't have any powers that are skipped, so I'm not going to worry about it. Now, a little different with a polynomial because you have these multiple terms. You're going to look at the first term of the divisor and compare it to the first term of the dividend. And what you want to do is make sure that you will be able to create a perfect match for those through multiplication. So I would need to multiply x squared by 3x squared in order for it to match the first term in the dividend. So since I'm going to multiply it by 3x squared, I'm going to write that above its like term in the dividend. So I'm multiplying this by 3x squared. Now this 3x squared is going to multiply my entire divisor. I'm going to distribute this 3x squared into both of them and write it down. So I have 3x to the 4th minus 9x cubed plus 15x squared. And like I would do with constants, I would then subtract. Now, as I subtract and I've got multiple terms, make sure you change the sign of every single term as you subtract. Those first terms will always cancel out because you created a perfect match before you subtracted. And then when you continue combining these like terms, you'd end up with 4x cubed minus 15x squared. And like you would do with long division with constants, you bring down the next term. We're going to go back to that divisor and look at the first term of the divisor and compare it to the first term of this new kind of part of the dividend that I've brought down. I want them to be a perfect match through multiplication, so I'm going to need to multiply this by 4x. I'm going to write it above its like term, who happens to actually be the identical term. That's just random. And I'm going to multiply 4x into the entire dividend. Make sure you distribute. So you would have, or into the entire divisor. So make sure you distribute. This would be 4x cubed minus 12x squared plus 20x. And I'm going to subtract these. Since I'm subtracting, I do want to make sure I change the sign of all three of the terms. And then the first terms will cancel out. I'll combine like terms vertically, and I'll get negative 3x squared minus 16x, bring down one term. Again, I want to compare the first term in the divisor to the first term of the dividend. I want them to match. So I'm going to be multiplying by, looks like negative 3. That should be right above its like term. Since I'm like going down successively one power of x at a time, once you've got it kind of set up with the first part of your answer right here, first part of your quotient, each one of these should always be above a like term. All right, I'm going to distribute. I'll get negative 3x squared plus 9x minus 15. And then I will subtract these. And so I need to change the sign of all of the terms right there. And then I'll add vertically and combine like terms. So those are going to go ahead and cancel out. I'll get negative 27x plus 9. This is my divisor. Now, this is my remainder. When I write the remainder, you'll put a plus in front of it because these terms are all separated by a plus or minus sign. This would become the numerator of the remainder. Your denominator is your original divisor. And so this is your answer. You could rewrite it if you'd like. All right, so why don't you pause the video, try number 2. When you're ready, restart it, and you can compare with my work. All right, so I have my solution up on the screen. I think just kind of a couple things to watch out for. Placing part of your quotient as you go above its like term will help you know how many more steps you have to go before you're done with the problem. That is helpful. Sometimes you might feel like you aren't sure, am I done or not? Well, when you've reached kind of the end and there's no more numbers to bring down, that's how you know. Also, just watch for the sign changes when you are subtracting. Those are really easy to kind of miss. Once you can pay attention to those two things, oh, and also don't miss any declining powers. Pay attention, I guess, to those 3 things, and then usually students are very successful. Synthetic division is super nice. It's much faster to set up than long division. It also takes less space. Its limitation is that it cannot always be used. If the divisor is a binomial with only 3 terms and the highest power of x is 1, then we can use synthetic division. But if you have multiple, like, a trinomial that's your divisor or something like that, or if your divisor has a power that's higher than x to the power of 1, you're not going to be able to use synthetic division. You'll be forced to use long division. So there are steps here kind of written on the side. Different people do write their synthetic division differently. I write the synthetic division the way that you'll see kind of in the sample on here. Some teachers put like their boxes in different places. Don't think that like, oh, one person is right and one person's wrong. Honestly, it's kind of regional. Kind of depends on where you learned and where your teacher maybe learned it from. So you're being impacted a little bit here from where I learned math and where I went to school. So, and some of our other teachers are going to express this a little bit differently, but you're going to get all of the same results. So don't let that stress you out. So when you're using synthetic division, when you're dividing, what you want to do is you want to start by taking the root of the divisor. Whatever factor we're using as the divisor, take the root. So make sure you change the sign here. Notice it's not a -5, it's a +5. Then we're going to use the coefficients from the dividend, including their signs. And if you have any powers that are skipped, you would need to have a 0. You bring down the first number, and then you will multiply by the root, add it, get this new result, multiply by the root, add, multiply by that root of 5. This last number here is always going to be your remainder. Sometimes the remainder is 0. The part that's left, starting from the right-hand side, would be your constant. After that would be your linear term with just an x. Then your quadratic term as I move from right to left. If we had more terms, we'd have a term with an x cubed, x fourth, and so forth. Okay, so let's just try some of these. So on this one, here's my divisor. Oops, sorry, I thought I was highlighting, and I definitely was not. Let's try again. Right here. So for this divisor, here this root, or the 0 of this divisor, is -3. And I'm going to use all of the coefficients of the dividend, just ensuring as I go that I'm not skipping any powers of x. The first number is brought down. And then each time I'm going to multiply by this root right here in the box. So whatever's at the bottom will be multiplied. So I'll get -6. I'll add. I multiply again by the root of -3. Watch your signs. I'll get 15. Add. Multiply. And again add. Now this last number right here is your remainder. In the example that was provided earlier, the remainder was 0. So we didn't write the remainder. But in this one, we do have a remainder. 7 is the constant. The -5 is your linear term. X to the power of 1 is called linear. And then the one in front of that would be your quadratic term, or x squared term. And then for the remainder, I have a -16 over the original divisor of x plus 3. Notice I use the x plus 3. I'm not using the root of -3. I'm using the original divisor here. All right, so why don't you go ahead and pause the video and try this one and then compare. And here's my worked out solution. Just kind of watch out for this 0 right here. Once you've done synthetic division a couple times, it'll all come back to you from last year, and it's something that you'll be very successful with. Okay, the factor theorem of polynomial functions. What the factor theorem says is that if x minus c is a factor of some function, we could call the function f, then when we divide, we'll get a remainder of 0. It'll fit into it perfectly. There won't be any leftover values, which is why it has a remainder of 0. Also, we could describe the root of this factor. This root would be positive c. It is a 0. It is an x-intercept. It is a solution. It is a root. And finally, I think the most interesting thing is that if you take f, the function f, and you evaluate it at any of its zeros, okay, any of its roots, you will always get a value of 0. Now, let's think about why that would be. When we find roots and zeros, what we're finding are x-intercepts. However this function might look. Whoa, that definitely was a miss. What's the height of all of these? The height of all of those is 0. And when you're finding f evaluated at something, you're finding the height of the function at that specific x value, which is why you're going to always get a 0 on those. So that's what the factor theorem says. So taking a look at example 5, consider that we have some polynomial that we're going to call g, and there's this expression. You might notice that the coefficient of the linear term is represented with a variable c. So c is some unknown number. Now c is just a random letter. We could have picked a for alt or whatever. So it's not related necessarily to the c in the factor theorem. Okay, so just random that I chose that. So c is an unknown real number. If x plus 3 is a factor of this polynomial, then what is the value of c? Well, there's certainly more than one way to go about this. Okay, one way to go about this would be to try to use synthetic division and to figure out what would we need to get a 0. So I'll explore that. We can consider that. Since the factor is x plus 3, the root is -3, I'll take the coefficients, making sure that if I skip any powers of x, that I represent them with a 0, but this time all those declining powers were there. And then you bring down the first number and you repeatedly multiply and add, multiply and add. So when I add this, I would get c minus 9. Interesting. that c minus 9 needs to be multiplied by 3, which would be negative 3c plus 27. And when I add that to the 15, it's supposed to equal 0. So negative 3c plus 27 combined with the negative 15, I guess I can combine that right away to a plus 12, should equal 0. So negative 3c should equal negative 12, and c must be 4. So that's one way to do this. It's a great way to do it. Nothing wrong with that. So using synthetic division. Another way is to use this kind of interesting idea that the root, which in this case, the root of g that we know is at negative 3, is supposed to equal 0. That's supposed to equal 0. So when I plug a negative 3 into this expression, I should get a 0. So if I substitute in a negative 3 in for all of these, I should accumulate to nothing, to a 0. So if I plug in a negative 3, I would get 81. Let's see, negative 4 times 27. I'm not feeling like working that hard, so let's just see what that would be. Negative 4 times negative 27, or negative 3 to the third power. Evidently, that is 108. And then minus 18 times negative 3 squared, or 18 times 9. I'm not really sure why I decided I needed to write this all out. I probably could have used the calculator a bunch more. Negative 162. And then remember, x is negative 3. So this is minus 3c and minus 15. And this is supposed to all equal 0. But it's just an equation I could solve. So if I combine all the like terms on the right-hand side, I have a whole bunch of constants. 81 plus 108. And then minus the 162. What else was there? And it looks like minus 15. So if I combine all those like terms, those combine to 12. I feel like we've seen that number recently. So negative 3c plus 12 should equal 0. I'll move the 12 over to the other side and starting to see some familiar stuff, and I end up at c is 4. So which strategy is better? Whichever one you understand better. So pick the one that you like and use it. All right. Let's take a look at this next part, the remainder theorem of polynomial functions. So this is kind of interesting. When you divide, maybe you divide by something, and maybe what you divide by is not a factor that goes in evenly. So there is a remainder. Well, whatever that remainder is the same as the value of the function evaluated at that number, which is interesting. So this can allow us to find values of something without maybe having to do a whole bunch of computation. So let's just take a look at this one. So if I wanted to find f of negative 4, one way that I could do that is I could plug in or substitute in a negative 4. Now, if I had a calculator, so it's not really that big of a deal. Without a calculator, I could still do this. But, so this is the substitution method. And then I could find out what f of negative 4 is. Okay, totally doable. Maybe not like my favorite thing on earth, but I could do it. Well, if I wanted to find f of negative 4 a different way, what I could do is I could take that value of negative 4 and I could plug this in as the root and use synthetic division here. Now I do want you to notice I'm using negative 4 here. That kind of matches because this in the factor would have been a minus c, but here it's a positive c. So I am using the one that's already had the sign change. That's what I'm using here. So I'll just use some synthetic division. I'll get 3. So I'll multiply and add repeatedly, hopefully correctly. Let's see, what would that be? 80 and 28, maybe 108. I don't know. Let's verify that. 27 times negative 4. Fantastic. Okay. And so then the remainder here is negative 105. So that should be the answer for f of negative 4. So I'm just going to verify this here really quickly. So I would have 3 times negative 64 plus 4 times 9 plus 20 plus 3. So let's see. Let's see, 23 and 36. And what is this? Negative 192, maybe. So negative 192 plus looks like 59. Oh, I think I got a wrong answer somewhere, so I wonder if I messed up. Somewhere I messed up. I'm going to pause, see if I can figure out where I messed up so you all don't have to sit here and listen while I do that, and then I'll come back. All right, took me a little while. I figured it out. I didn't substitute in the right number here. So we're plugging in a -4 and not a -3. So I had some wrong values, but when it ended up and we compared, we got the same answer each time. So clearly for me, because I make a lot of computational errors, synthetic division is going to, for me, be a more effective way to do this than using substitution, although both would work. All right, looking at number 7, we want to solve this equation. What we know is that -1 is one of our zeros. Now, what does it mean to solve an equation? To solve an equation means to find x. That's what that means. And in this problem, since we have a degree 3 polynomial, we should have 3 different answers for x. Now, some of them might be real, some of them might be imaginary, but we need to find all 3 of them. So I'm going to start off with the fact that I have already one of my zeros. I'm going to use -1, which is one of my zeros, into this expression with synthetic division. And I do have all of the powers here declining. I don't have any that are skipped. And I'm going to find out what would the polynomial expression be if I divided out the factor x plus 1. Essentially, that's what I'm doing. So I would get 15. I'll multiply and add, hopefully correctly. We've already seen that I've not done a great job with that a little bit today. And I end up with a remainder of 0. That's important. If I did not have a remainder of 0, I would know I would make an error. X equals -1 is a 0. I have to have a remainder of 0 here. So what do I have left? I have left the quadratic 15x squared minus 1x minus 2. And I want to solve this to see, where does this one equal 0? Well, looking at this one, it might factor. It's totally plausible that it factors. We could kind of spend some time factoring it. I'll maybe give it a little shot real quickly. If I can find one, awesome. If I can't find any factors that work, then I would be using the quadratic formula instead. All right, I'm going to split 15x squared up into 5x and 3x, because whatever are in these two spots, when you FOIL back, would multiply back to 15x squared. Now, the only factors of 2 are 2 and 1, and I could play around with the various signs. And so where I place them is important. So like wherever those get placed, as I FOIL out, these two would get multiplied together. And so with these, and they would form like terms and would combine. My goal would be to combine to this -1x. And if I play around with signs, sometimes I can get there. Well, that didn't work with what I have right now. But maybe if I switch the locations of the 2 and the 1, I'll end up with a 5x and a 6x. That can get me to a -1x if I make the 6x a negative. So this would have to be a negative. This would have to be a positive. So that's how I factored it. Certainly, the quadratic formula could also be used. And then I'll solve this. So x would be 2/5. So you change the sign of the constant. You divide by the coefficient of the linear term. And here x would be -1/3. So if I want to then solve the equation, I want to find all 3 values of x. We already knew one of them. X is -1. The other 2 are 2/5 and -1/3. Now, if this couldn't factor, I would use the quadratic formula. It is plausible that I might use the quadratic formula and not get real number answers. You've seen that before in Algebra 2, and that's possible here as well. And that is the end of our notes for this section.